So this section is on rotational motion. Rotational motion is has many similarities with translational motion, but instead we use angular variables instead of translational variables. And so when we were studying translation in an earlier chapter, we talked about position, which we represented with x, and then velocity, which we represented with v, and then acceleration, which we represented by a. And for the angular variables, when we're talking about rotating systems, we talk about the position as an angle, in this case theta. We use theta to represent angle. And then the angular velocity, which is the rate at which something rotates, is represented by omega. And then the angular acceleration, which is the rate of change of the angular velocity, is represented by the variable alpha. So for units, we'll usually measure theta in angle in radians, right? Whereas we measured position in maybe meters, right? And then we'll measure angular velocity usually in radians per second, but not always, maybe revolutions per minute, just like we measured velocity in meters per second, right? And finally, we measure angular acceleration in radians per second squared, just as we measure, similar to the way we measured acceleration in meters per second squared. So just as velocity in the translational motion is change in position over change in time, the angular velocity, omega, is the change in angular position over the change in time. Similarly, in translational coordinates, we have the acceleration is the change in velocity over the change in time. And in angular coordinates, we have the angular acceleration alpha is the change in the angular velocity over the change in time. Notice that these formulas are very similar to each other, right? This is the angular position, this is the translational position, this is the angular velocity, this is the translational velocity. These formulas look just alike except with the letters changed. And what you'll see as we go forward is that the formulas that come out for angular kinematics look very, very similar to the formulas that come out for translational kinematics. So for translational motion, we could say a car travels 20 meters in 4 seconds. What is its average velocity? And so we just grab our velocity formula and we say velocity is change in position over the change in time, and that's 20 meters over 4 seconds, which is 5 meters per second. And so its average velocity is 5 meters per second. If I wanted to be really careful about that, I would say, well, velocity is the change in x, so it's x2 minus x1 divided by t2 minus t1. And so I would assume it started at position x1 equals 0, and so I would say its final position was at 20 meters minus 0 meters over 4 seconds minus 0 seconds, which is, again, 5 meters per second. And implied in here, of course, is that it's plus 5 meters per second, which means it was moving in the plus x direction. Usually that's, to the right if we have a coordinate system that looks like this.